So let's consider the differential equation of this form. This is a differential equation of order n, where this represents the nth derivative of y with respect to the independent variable x, and this is also a linear differential equation. Now this linear differential equation of order n is normal for the given interval I if it satisfies these two conditions. So the first condition is the coefficient a0, a1, an minus 1 till an. If all the coefficient of y and its derivative are continuous along with the function of x, that is written as rx. So this function along with these coefficients, if they are continuous on the interval I, with the second condition that if the leading coefficient of the differential equation, means take the highest order derivative, whatever the coefficient is associated with that derivative, if that is not is equal to 0 for any value of x on the given interval, then the differential equation is normal. Now before beginning with the examples, let's take a brief overview of some continuous functions or well-known function when they are continuous. So starting with the first term, that is polynomial functions are continuous everywhere for each value of x as a real number. For example, if I take this polynomial, so this is a polynomial, it is a cubic polynomial, and this is always continuous for every value of x belongs to the set of real number. Next is a rational function. So this is also called as a rational function where the numerator and denominator are the polynomials. So this type of function is continuous function except for those x naught where your denominator term is 0. For example, if I say that x square plus 5x upon x minus 2. So this rational function is continuous whenever x minus 2 is not is equal to 0. Or we can say that for x is equal to 2, this is a discontinuous function. So what is the range of x? So x belongs to the set of real number minus 2. For these values of x, this function is always continuous. Next is a root x. So this root x function is defined as well as it is a continuous whenever x is greater than or equal to 0. Otherwise, you will get a complex number. So right now we are dealing with the real numbers. So we will get a real number whenever the x is greater than or equal to 0, and even in that case the function is always continuous. But let's take an example. If it is written as x minus 5, so this function is defined as well as continuous for all x greater than or equal to 5, because this quantity must be greater than 0. If this quantity is greater than 0, so we are getting a condition as x is greater than 5. So for every value of x greater than or equal to 5, this function is defined as well as continuous. Next term is a sin x and cos x. These two functions are defined as well as a continuous for every real value. Whereas tan x or a secant x is continuous everywhere except x is equal to 2 times of n plus 1 pi by 2. So this is a pi by 2, where n is any integer. And cot x and the cosecant x functions are continuous everywhere except x is equal to n pi. Again, n is integer. So the next is a log x. So log x is a continuous function whenever x is greater than 0. So if I say log of x plus 5, so this is a continuous function whenever x plus 5 is greater than 0, or we can say that x is greater than minus 5. Whereas the exponential function is continuous everywhere, whatever the value of x we will take as real. Now we are moving towards the example. We will find the interval on which the following differential equation are normal. So we have two conditions. We need to check whether each and every coefficient are continuous as well as the leading coefficient is not is equal to 0. So in this case, let's write a naught x. So the starting coefficient is 1 minus x square, a1x, that is equal to minus 2x square, a2x, that is the next coefficient, that is n into n plus 1. Now right hand side function rx, that is equal to 0. So this is a polynomial. This is again polynomial. Now this is an integer because it is given as n as integer. Right hand side is a integer. As we know that the polynomials are always continuous for every value of x. So from here we can say that these functions are continuous for all x belongs to the set of real number. Now, second condition is a naught x is not is equal to 0 for any value of x. So for that, check when 1 minus x square is 0. So 1 minus x square is 0 when x is equal to 1 and minus 1. So for these two values, we are getting a 0, but we need not is equal to 0. Therefore, we will remove this set of values from this set of real number. So we are getting an interval as on which this differential equation is normal, that is a set of all real number except 1 and minus 1. So on this interval, the given differential equation is normal. Similarly, find the interval on which this differential equation is normal. So let's write the coefficients first. A naught x, a1x, a2x, a3x and rx. So a naught x is x cube, a1x is 9x square, a2x is 18x, a3x is constant 6. Your right hand side x is 0. So all these are the polynomial and polynomials are continuous for every value of x belongs to the set of real numbers. So till now we are getting an interval as real number. But there is a second condition. Second condition says that a naught x is not is equal to 0. So what is the value of a naught? That is a x cube. So this number is not is equal to 0 when? For all values of x except 0. So x should not be is equal to 0. So finally we are getting the interval as all set of real numbers except 0. So on this interval, the given differential equation is normal. So in the next example, let's calculate the coefficients first. A naught x, that is equal to 1. A1x, that is 3. A2x, that is root x. Then we have a rx function as a sin x. Now in this case, this is a continuous function for every value of x. Same for this one. But this function is continuous when x is greater than 0. So what about the sin x? So sin x is a continuous for every real number. Right now we are getting a one condition. If x is greater than 0, then these all functions are always continuous. Now what about a naught x? So a naught x is 1, that is not is equal to 0 in any value of x. So overall we are getting the interval as for x greater than 0, the given differential equation is normal. Let's take another example. In this case, a naught x is equal to 1. A1x is mod x, A2x is 1 and Rx is x into log of x. Now in this case, mod x. So mod x graph is like this way, and this function is defined for every value of x. Moreover, it is a continuous for every real number. So mod x is continuous for every real number. So right now, from these three we are not getting any condition on our x. We can take all set of real numbers. Now what about the Rx? Whether this is a continuous for every x belongs to the set of real number? So answer is no, because this is a well defined, but log x is defined when x is greater than 0. So in this case, it says that x belongs to the set of real number, and in this case, we are saying that x is greater than 0. So intersection is x is greater than 0. Now what about the initial point, that is a naught x? Whether this is not is equal to 0? Yes. So this is always not is equal to 0. So we are getting only one condition, that is x greater than 0. So final interval is for x greater than 0. The given differential equation is normal. For E and F part, comment below for which interval the given differential equations are normal.